Who's sharing that slide? Aaron's sharing that
It's
slide.
me. Do you want to share your slides so you can switch
Sure.
slides with okay, go for it. We're at
Oh,
the top of the hour, but we'll maybe give folks another 60 seconds to connect up or so. All right. Well, good morning, good afternoon, everybody. Hope everyone's doing well. I'll go ahead and get started as we still have folks filtering in. Um, so we'll go ahead and Travis, you were going to start us off with a couple slides summarizing AGN SIG
right.
activities, and
Yeah,
then we'll move on. So go ahead.
great. Well, all right. Good day, everybody. It's May 26th. And before we get into our Vision Series presentation by Stéphanie Juneau, I wanted to just have a couple of slides to discuss. We had a COPAG retreat, which was a lot of the different SIGs and STIGs that met up with the program office, the NASA's COPAG program office, as well as the executive committee of folks that are leading the COPAG. And so I just wanted to talk about some of the takeaways that they had for the AGN SIG community, in that we had a discussion of how can we as a SIG help out the COPAG, and then alternatively, what can the COPAG program office be doing to help out the SIG? And so one of the immediate conversations that we had of like, where is astronomy going in the near future is it could be facing some bumpy roads ahead because of the lack of funding that's available for um, any sort of a professional position, such as like postdocs and grad students. And one of those reasons is due to a lack of funding through NASA operations. And so what the program office wants to do then is try to keep us abreast of any sort of opportunities, funding opportunities that we might not necessarily be used to. So one example would be maybe we're interested in a particular wave band that would be useful for observing from the moon. And so maybe there need to be a study that talks about understanding like the viability of looking at that wavelength from the moon. And so there could be a potential call for doing something like that. And that would be one different alternative avenue for funding that we, as maybe the typical astronomers, are not used to applying for. Second, we'd like to have the program office folks stop by once in a while because overall, this is a NASA-based community discussion group, science interest group. And so we'd like the community to feel that this is rooted in NASA. And so seeing and hearing these folks and understanding the relationship that of what we are doing here in these monthly seminars, and how and what these seminars do to impact the program office at NASA, I think would be an improvement for us and help keep that connection strong between us and the program office. And then lastly, we're looking to start opening up a volunteer form for talk submissions. So one thing that we find it difficult to do is to stay up to date on all of the amazing papers that are coming out so frequently. and then having an idea of who we would want to be inviting for spotlight presentations. So one idea that we submitted to folks is to create a standardized submission form that you could select. I want to give this type of talk. It would be relevant for this type of SIG. Here is potentially a paper that is relevant that maybe just got published, and I'd like to talk about that. And then that would come to us and allow us to create a reserve of viable presentations that we could be selecting from to then bring to the community. So I thought this was kind of akin to like when you get a paper published, ideally what the first thing you do is submit that paper to archive, and then hopefully in the future, the second thing you do is then submit a volunteer form to speak about that paper to a relevant SIG. So we'd be looking to bring something like that online within the year. So in providing this help to the SIGs, we'd also want to give back and try to be more constructive in our conversations that we have relevant to AGN. And so what that means is in the future, we'd like to focus the ends of our presentations to be discussing more about what the mission needs are relevant to NASA. So we want to start asking folks more often, like, well, what kind of observatory would you need to be able to answer this question? Maybe we're not sensitive enough right now. Maybe we don't have the resolution right now. We don't have the right wave bands. What do we need in future missions to be able to come up with a better plan that's relevant to AGN science? So that's something that you can look to hear more about in future talks then, as we help try to figure out maybe how we can contribute to the Astra Initiative. And so, again, the Astra Initiative is this near-term opportunity that has a call for early concept mission or maturity level programs that's due at some time next month. This is still potentially nebulous to you and me. So I guess this is just a reminder that we need to be coming up with these concepts at a early but meaningful level to potentially come up with really cool idea or observatories that could be furthering AGN science. And so the question is then, should we have a special session on Astra? And we would want to discuss what concepts would best serve the AGN community, and what technology gaps or wavelength coverage should the COPAG hear about from us. And if you'd be interested in having a special session on Astra, we'd really like to hear from you. It takes some time and effort to put this together, so we'd really like to have an interested base before we dedicate some more resources to this. So please reach out to Aaron or myself if you have any sort of wanting to get your ideas thrown in the hat about a future mission that could potentially be looking at viability studies then by the beginning of next year. So I'll leave it there, and thank you very much for that. But then I'll pass then to Dr. Stéphanie Juneau, who will be talking to us today about AGN science in the era of big data from DESI to the AI revolution. Stephanie, thanks so much for coming to talk with us today. I really appreciate it. And I'll let you have the floor.
Sounds great. Hi, everyone. Thanks for the invitation. So I'm going to go ahead and share my screen. Oops. Let me go back to my top slide. Okay, so, right. Yeah, so I was thinking, so all of this will be space-based, but I think it can really inform the conversation. So what I'm hoping with this talk is to spend about 30 minutes or so giving you some updates about what's happening with large-scale surveys, and I will use DESI as an example, not just because it's a comprehensive study of the field, but then I want to touch a bit more on machine learning AI, and let's just get started here. Okay, great. So first, setting the stage, I think for people who are joining here this call, you probably already work in related fields, but so we all on the same page again. Why do we think black holes are closely related to their host galaxies? So there are at least three different reasons. One is scaling relations. For example, the black hole mass is quite tightly coupled or correlated with some host galaxy properties. So sigma is often used as the cell-velocity dispersion of the bulge of the host, but often we also look at the total mass of the galaxy. So it seems that black holes and galaxies grow together. And then if we study them across cosmic time, and if we measure the total growth of galaxies, so their star formation rate on average across cosmic time from high to low redshift, we find that galaxies, grow, peak around redshift 2 or so, which is the cosmic noon epoch, and then decline. And then if we separately look at the total growth in supermassive black holes, and this could be done from X-ray, infrared, optical, various wavebands, but we also measure the volume growth through cosmic time, we see a very similar shape, different normalization, but kind of similar shape, where at least this is telling us that on average, supermassive black holes and galaxies were growing at the same time also, like through cosmic epochs. And lastly, we think that there's actually a pretty tight physical connection in the sense that in numerical simulations, we tend to produce overmassive galaxies without the presence of AGN feedback. So we think we need to have some sort of AGN feedback to basically regulate galaxy growth. So this is more so from the simulation side than from the observation side. But these are all different reasons why we think that black holes and galaxies are related, and how we can basically learn more about galaxy evolution and black hole evolution together. So I wanted to step back and think, okay, what are still big questions? So how did supermassive black holes form? So how do we start from black hole seeds? When and how do they grow? So when we have an AGN, so an active galactic nucleus, how is that triggered? What's the duty cycle? What fraction of time is it growing versus a dormant black hole? And I just was mentioning feedback, but how does that work? Like, how do we measure the impact of AGN on their host galaxies? And then I was thinking, well, none of these questions is new. Like, these questions have been around for a long time. But I don't think we fully have an answer still to any of those. We've made a lot of progress. We keep learning more, we keep making progress, but we still don't have final answers. So I was thinking, why is that? Like, what's going on? So I want to just reflect on this. Oh yeah, sorry. And then another aspect, which I won't get into too much with just 30 minutes today, but how do these active galactic nuclei work? Because so far, a lot of this is, okay, we grow black holes, and we know that they grow by merger or by accreting material, so in the AGN phase. But what's the actual astrophysics? And we know that they can launch radio jets. How does that all work? So there's a lot here that needs to be understood. But what I want to do is still reflect on why is it that even if we just look at the first three questions, we still haven't finished answering them, quotes. So one challenge is that AGN are very much so multi-scale and also multi-phase if we look at the detail of what's happening. So I really like this diagram. This is from a recent review that I encourage you to take a look at if you haven't yet, by Dave Alexander et al. What drives the growth of black holes? A decade in progress is the review. But this diagram, this is obviously a cartoon, but it shows kind of a representation of what do we have to deal with here. So we have the black hole with the accretion disk. It can have a radio jet sometimes. Then there's a corona, and then there can be winds from the disk. There can be outflow. But then if it's an AGN, it means there must be some kind of inflow to fuel this accretion disk. And then we're dealing with, this is milliparsec to parsec to kiloparsec to megaparsec scale, because in the end, the inflow come from larger scale to increasingly smaller scales, but the outflows and impact go the other way from the small scales to very large scales. And this is even without knowing yet, what's the shape of this torus, what's the, all the details of that. But then we do know, however, that there is, even beyond the gravitational radius of influence of the black hole, because of these outflows and this radiation from the disk and jets, they can be very far-reaching impact to kiloparsec scale in the host galaxy, all the way to even outside in the case of jets that deposit energy in the CGM or IGM regime. So I think the fact that we have to deal with such a multi-scale situation makes it very challenging, of course. And then it's also another aspect of that, and I think it's good to remind ourselves, is AGN are not necessarily objects. They could be an event. So sometimes the AGN is on, sometimes it's off for the same black hole. And this switching on and off is a different time scale compared to the host galaxy time scale. And I like this figure here that Ray and Hickox put together, but it's actually work from Greg Novak using from a simulation. You can see the variation in the Eddington ratio. So you can see the accretion rate variation. And sometimes there's these peaks where you would say, okay, now this is an AGN. But when it's a very low accretion, you would say, well, this is not an AGN here. This is just a black hole is there. But it's not as simple as saying, okay, this galaxy is an AGN or it's not. This is like a current AGN phase. So we have to basically keep this into account as we study AGN and in relation to their host galaxies. And lastly, we have to deal with obscuration. And the obscuration can come from the torus, which would be very small scale obscuration. And I put torus in quotes because I don't want to assign necessarily a shape to this, but it's like a material in the equatorial plane and that can obscure the central accretion disk depending on the line of sight. But it can also be obscuration from the host galaxy, and this could change depending on what's happening to the galaxy. So for example, gas-rich major mergers, create this cocoon of gas, and this can increase the obscuration. So this is not to discourage us, but I think these things explain why we're still, pursuing some of these questions that we've been studying for decades. And I'm going to talk about some recent results, and then I'm going to go back to these questions at the end and reflect a bit on what's the progress and what is next. And then, so the focus for today is I wanted to say, okay, how can we leverage these very large astronomical surveys? And I'll spend a bit more time on this, and I'll have a bit less time, but I do have a bunch of backup slides on machine learning and AI, so you can ask me more about this. But also, how can we leverage these new techniques? So astronomical surveys, usually they either have a wide area, very wide area being a bit shallower, or they can be not quite as wide, but quite deep. And we do need both kinds. Ideally, we would want both, very wide area and very deep, but that's not always feasible. So normally we have to compromise. But what do we get from these surveys? So they're key to conduct large population studies. So this is important to understand, how do black holes grow, like on average, what fraction of the time is it on or off? Because we cannot follow on a human time scale, follow these phenomena that are happening on, millions of years or more or longer. And then we also can leverage these big astronomical surveys to find very rare objects or short-lived phases. So rare objects is something like the most luminous quasars, for example, like the record breakers, the highest redshift. And then short-lived phases is, we just discussed, AGN can switch on and off, or they could be a very special case, like a very deeply embedded obscured phase, and this might be more short-lived. So then it's really important to have a bigger statistical sample so we can find and identify these objects. And then as far as surveys, this is a very incomplete list, but for AGN in particular, we can leverage, optical spectroscopy, X-ray surveys, and then time domain. This could be in different wavelengths. So I have a couple of optical and I guess there's some infrared too with WISE that's not listed here. In the infrared, we can trace the hot dust. And in radio, of course, this is to help us with finding the percentage that have a radio jet. So I will highlight the case of DESI, but I really want to stress that this is just one example survey among many others. And then what about machine learning? And now we hear a lot about AI all the time. And we hear about, okay, machine learning and AI. So I want to clarify a couple of things here. So machine learning in astronomy has been around and it's been used for a very long time. Like, for example, some of you might have heard of PCA. This was applied specifically to quasars, for example, like decades ago. And so far, I would say for AGN studies, mostly machine learning techniques have been used for classification, outlier detection, but there's a lot more that we can do. And for this, I think it's really a question of like the tip of the iceberg. And machine learning itself is entering its new era. And that's why I think it's often more conflated with AI, because it starts using the same underlying architecture. So for example, transformers and foundation models, these are what those large LLMs use, like ChatGPT and Claude and all these things. But these same basically algorithms now are being used for machine learning as well. So it means that the machine learning are a bit more AI-like now. But it also means that we have a lot more tools like under our belt that we could utilize, but we have to do this the correct way. Okay. So about DESI. So DESI stands for Dark Energy Spectroscopic Instrument. It's a highly multiplex spectrograph, 5,000 fibers, and it's on a 4-meter Mayer telescope. And eventually, it will have 70 million. It will have spectra for 70 million distinct galaxies and quasars. And it was just extended to an 8-year survey. However, we have just completed the first 5 years, so which was the original plan to do 5 years. And we already have spectra for 47 million galaxies and quasars. These are not ready to use now, but we already have 3 years that is ready to use, and we already have the first year, which is publicly available. So anyone here can also use the first year of data. And then in this particular survey, and also building kind of from the legacy of, for example, Sloan, the SDSS, we know that optical spectra of large numbers can be used for a very wide array of AGN science, including finding interesting objects that we can then follow up with space mission like HST or JWST or others. So I have here, again, an incomplete list. But with DESI, we've already, and I will say a bit more about this, but we've been using this kind of unprecedented data set to search for AGN and dwarf galaxies, measure the, large catalogs of black hole masses, find changing look AGN, which are rare phases. We have to basically catch them in the moment of switching on or off. And then searching for kind of more rare red quasars. So red quasars still have broad lines, but they're very redded. And it turns out that most likely it's because of a special evolutionary phase and not because of Taurus obscuration. Also, the DESI data has been used to currently study AGN-driven outflows and then study host galaxy properties. And some of these result in catalogs that are also publicly available. So again, anyone who's called is welcome to use this. And then a more recent paper on using machine learning to identify AGN, kind of going a bit beyond the usual emission line diagnostics. So this is a kind of at a glance. And I think I might skip this for time. Yes. So I will, after the talk, send a link. You should watch this. It's a pretty cool animation. It shows the 5-year progress of the DESI map. It's really very nice. Okay, but I want to go back to the same questions I had at the beginning. And I will spend a bit more time on the first one, very little time on the second, and then mention a couple of things on the last. But how did supermassive black holes form? What are the black hole seeds? This diagram, you might have seen this before, is a cartoon to show the different scenarios. So we can have pop tree, very light seeds, like individual stars, all the way to direct collapse, which are the heaviest seed, like 10 to the 5 range in solar masses. And this cartoon illustrates this concept that it is quite possible that some of these early seeds, in the cases where the galaxies have not interacted too much, have been preserved as leftover artifacts, basically, that we could find in the form of intermediate mass black holes, even now at no redshift. And this is a motivation to search for these intermediate mass black holes in dwarf galaxies. So, what I want to do is highlight some work about this. First, I think this is the first systematic study was done in SDSS by Amy Rines et al. And looking at dwarf galaxies, meaning less than a log mass of 10 to the 9.5, which is about the Large Magnetic Cloud, and using the BPT, which you see here on the right-hand side, and including AGN and composites as cases with AGN, and similar work with either SDSS or gamma, this results in a dwarf agent fraction of 0.5%. So only 0.5% of dwarf galaxies have an AGN according to this. And then a total census of between 200 and 1,000 intermediate black hole candidates. So what can we do with DESI? So this work, it was led by Ragapucha. This is a paper from last year with DESI early data, which is validation data, and just 20% of the first year. So if we use the same BPT diagram and use now the DESI spectra, what do we find? This is the stellar mass of the host galaxies for dwarfs, so up to 10 to the 9.5 versus redshift. And this is all just for the AGN and composite the AGN candidates. So what you can see is that DESI in blue has many more, we find many more AGN and dwarf galaxies, both extending to lower stellar mass hosts and also going to higher redshift. And specifically, this was basically finding triple the AGN census for as far as the number, but now with the DESI DR1, we actually have 10 times more than the pre-DESI census. So with DESI, we're already with 1 year, we're making a jump by a factor 10 of how many AGN we can find in dwarf galaxies. And this is just finding them. So there's a lot more room for studying them in detail. But I also want to mention something else that's pretty interesting. If we look at what's a fraction of these dwarf galaxies within AGN, we found about 2%. Compared to 0.5%, this is 4 times higher. So what's going on? This is not just finding more of them. This is finding a higher fraction. So the main explanation that we found is if we compare, let's say, with the Rhine sample from SDSS and a DESI sample, if we match them to have the same magnitude and the same redshift range, we still find more AGN, but we also find them toward lower luminosity. This is the AGN luminosity here. And the reason that we think is the most likely explanation is that the DESI fiber is smaller. So this is the angular size of the DESI fiber compared to SDSS on a this is just one example dwarf galaxy here. But basically, by having a smaller fiber, we can better isolate the emission line signatures from the AGN from the rest of the galaxy. So we think that this is why we can get a 2% AGN fraction, even if we control for the same parent population. Okay, so now I want to move on to understanding using the scaling relation between the black hole mass and the galaxy mass as a tool to better understand what is the most likely black hole seed formation scenario, and also whether we can start understanding evolutionary tracks between the growth of black holes and the growth of galaxies. So we're going to be looking at the black hole mass as a function of the galaxy stellar mass. And then, so this is work here by a recent paper from a couple of years ago. And then in this case, they're trying to understand, like, if they look at galaxies at different redshift, what's the most likely trajectory of how they would grow toward the redshift 0 relation. But what we've also been seeing a lot in the literature now is overmassive black holes. So I want to talk about that as well. So this is here, this is work also led by Ragapucha, and this is now on the DESI DR1 paper, which is just finished, so it should be on the archive, I think, next week. But what you can see is if you look at the black hole mass and stellar mass relation, and then the left-hand side is it's all galaxies where we're confident we can well resolve the host galaxy, it's extended, and we can measure its stellar mass. As a quick note, the right-hand side, these are point sources in the imaging, so they're more quasar-like, so we're not sure if we fully measure well their stellar mass in this case, so we consider the stellar mass more uncertain here. So if we focus on the left side, so that, there's a fairly tight relation, which is not too new, and you can in fact see that the normalization is quite similar to previous work, so the new work is in orange here. And then what I wanted to highlight is that what we've been seeing in the literature recently is a lot of results from JWST at high redshift. So these are these kind of purple kind of color point, magenta point up here. And then this magenta line is a fit to these high redshift JWST points. And then even at intermediate redshift, Mar-Mesqua et al., they've been finding also samples of these overly massive black holes. So these are cases where the black holes seem way more massive from what you expect with the host galaxy compared to the normal relation here. So with DESI, we're not finding a lot at all. Even if we were to consider these point sources, which we don't really trust fully the stellar mass, we're still not finding a ton of these like overly like massive black hole compared to high redshift. So there's definitely still an open question here about what's going on with these objects. But there is an interesting trend that we see in the DESI data, which is if you notice the shape of the contours is a bit of an extension here. And in fact, for the point source, there seems to be almost like a bimodality in the distribution of the black hole mass. So what is this? Is this an artifact? Is this because DESI has such a large sample that we start to see two different subpopulations, which is, I think, what we think. But what do they, one way in which we found two populations, and this is again Raga's work, is if we examine the spectra and then fit them and we fit the emission lines, the top part is for one example broadline AGN, with H beta and H alpha have a broad line. And this is a very typical representative example. I mean, they're not always like beautiful signal to noise, but it's like a kind of pretty normal like black hole line width here, broad line width. So the median is about 1900 kilometers per second for these cases. These are what we call the regular broad lines. But the bottom part, there's a subpopulation that have what we call extreme broad line. And the criterion here is just that the broadline is so broad that it starts to blend with the S2 doublet, which is on the right-hand side. And those have a median fluid half max of 4,700 kilometers per second. So, we were wondering, okay, we just have to treat this separately for fitting. But it turns out that what we can do is we split between extreme broadline and regular broadline cases, and we make again the same black hole mass stellar mass relation. We find actually two very distinct relations here. So these are, again, the DESI data in blue, and then the green is just these normal black hole on the left, and the light blue line is these extreme black hole candidates. And what's interesting is if we just fit the DESI data and we look at the blue, it starts to kind of go towards some of these overmassive black hole candidates that were found in other surveys at higher redshift. So what we're thinking as a possible interpretation is that maybe there are two different evolutionary pathways, and they may correspond to two different seed formation mechanisms. So the prediction for the light seed is that the relationship would just keep ascending to low mass, the same relationship. And this seems to be the case for one subpopulation of objects. So maybe on the left side, this would be the light seeds, but on the right-hand side, possibly they could be these overmassive black holes that come from heavy seeds that then would have their own distinct relation. So this is still subject to more work, and we probably need to compare with more simulations, but it's pretty exciting result. So with the first year of DESI, we have right now almost 10,000 dwarf AGN candidates. So this is really expanded parameter space. And then we're extending this mass black hole galaxy mass scaling relation to low mass, and possibly with evidence of two different evolutionary pathways, or possibly two different seed formation scenarios being supported. Okay, so just a quick, I'm not going to spend much time here, but when and how do they grow? So this case is understanding, which galaxies have an AGN on or off, and does this depend on galaxy properties? So to do this well, we need galaxy population studies, but also AGN studies and luminosity functions and so on. So because of the interest of time, I just want to mention that while this is not a result on its own, we've been building a value-added catalog that's already publicly available for DR1. And this is a catalog of all extragalactic sources in DESI, so galaxies as well. But it has an AGN classification and quasar classification, like multiple classifications, I should say, from optical emission diagnostics or infrared colors, including also quasars having broad lines, etc. So DESI has an interesting target selection function, though, so the redshift distribution is a little bit funny. But on the right-hand side, what you can see is these different colored histograms. Our red rock is the main DESI pipeline. So these are two different quasar classification, and VPT is at low redshift emission line, and WISE is infrared colors. So you can see that there's like many thousands in each of these little redshift bins. So this is a huge sample. So there's a lot of potential here for studying this question. And then we actually already are building the DR2 catalog, which will be even, so this first catalog is, I think, 17 million, and this will be 2 to 3 times larger for the second one. So I just picked kind of one quick highlight of things as something that DESI does well because of the large statistical sample is to look for changing look AGN. So SDSS was something like 20 years before DESI. So we have a nice, interesting baseline to find cases that the AGN switch on or off between SDSS and DESI spectra. So in this case, SDSS spectrum is in blue, so the AGN is on with broad line. And then the red spectrum from DESI, clearly it's been like more of a turn off case here. And with the DESI early data, we had found 56 changing look AGN, which is, not a huge number because there are now several hundred known in the literature. But with 1 year of data, we have a catalog of 561. And then you can see that they don't always change, like the changing look is not observed in all the same broad lines at the same time. There's actually to seem to be some kind of delay or evolution sequence between these lines. So this is pretty interesting because it suggests a broad line fading sequence, kind of similarly to the reversion mapping work. So this is just a quick highlight here before I move to the last part, which is how do AGN impact their host galaxies? Okay, so we know that they could, in principle, impact their host galaxies because there's a lot of energy available. So there's radiative energy, but also there can be winds or outflows. And then in the case of radio jets, there can also be a lot of mechanical energy being deposited. And all this AGN feedback can heat the gas, remove the gas display, so ionize the gas. In detail, there can be negative or positive feedback. So this example shows a Muse image with the O3 emission line tracing the ionized gas, and this is an AGN ionized outflow. And we know it's outflowing because this is from Muse, so we have a data cube, so we can look at the velocity, and then this animation shows stepping through the cube. And you can see that as you go to the O3 doublet, there's a very clear, we can almost see it like kind of coming out of the picture here. And if we look at the velocity and make a velocity map of this outflow, we have a very clear, the front cone is coming toward us, and then there's an active black hole behind this very dusty ring, and then there's a back cone behind the galaxy that we can see that's going away from us. So this is just one example. There are many such studies with Muse, but other IFUs. This is an exciting example at redshift 3. And then this is with JWST here with a near-spec IFU. And so this is a much more extreme case where if we look at, this is showing O3 in all these different velocity slices. First of all, what we can see is the ionized gas is very extended, but it's a lot of different velocity components. And I think this is a complicated case where they can also be like companions in this quasar at redshift 3. But as you can see, Well, again, this is just picking one example. But what we want to do is we want to combine or go from these case studies to get the bigger picture. So ideally, we want to do these spatially resolved studies, but combining with larger and larger surveys. So one other way to look at the extent of the AGN ionized gas is to map the narrowline region using imaging, which will so long-stretch spectroscopy, sorry, is another technique. So there's IFU, long-stretch spectroscopy, and then imaging. So how far can the AGN ionize the gas? So in the previous couple of decades, well, the previous decade, I guess, this has been studied now for at least a decade, and then there seems to be a relationship with the size of the ionized gas being much larger when the AGN is more luminous, going to quasar luminosity, kind of on the right-hand side here. And this is important for us to understand the capacity of the AGN to ionize the host galaxy, and also does it ionize all the gas that's available? So in which case it will be matter bounded, or is it just ionizing a small kind of limited region? And all of these previous studies of the size luminosity relation were done at low redshift, mostly due to limitation in observing abilities. But this is where with JWST, and this is work led by graduate student Sophie Lipovitz at Arizona, she was able to use JWST to isolate the ionized gas using, in this case, medium band imaging. So I think I'm tight on time. I think we started a few minutes later, but okay, I still wanted to give you the main point here. Okay, so with JWST, we're able to pick at cosmic noon this like redshift of interest where O3 and H beta are in one medium band filter, and then the next medium band filter as just the galaxy continuum. So we can subtract these, make the difference image, and it's tracing. Unfortunately, it's not O3 alone. It has H beta because of the filter width. But we can if we color it in green, you can see the ionized gas region. And we were able to do this so this is a paper from last year in 2025 for a small sample that still revealed for the first time, it still revealed 6 bicone, like AGN ionized bicone in these cosmic noon galaxies, but also while somewhat uncertain, it was still the first attempt to make the size luminosity relation at cosmic noon. So only a few points here, and then we're looking only for the one that are more convincingly AGN. So it's a small sample. But what we find is compared to the low redshift fit, which is this dashed line in cyan, there was a bit of a flatter trend in the points. And we didn't have enough of a large sample to really fit the trend, but we were able to use Muse data at low redshift to simulate what would we see if we put these Muse cubes, so we see all the details, at redshift 0. If we put them at the cosmic noon and we apply all the JWST and NIRCam, instrument signature, resolution, PSF, we apply these filters and we put the noise, what do we see? And it's this white dashed line. So one of the conclusions from this study is that we find that this dashed line is telling us that the actual ionized region could be at least 2 to 3 times bigger. And then with the instrument and NIRCam and the survey depth, we would see them like this. So that was interesting, but it was also telling us we need to revisit this. So Sophie was leading this work. Now she expanded to use a GEM survey with JWST, which does go twice deeper as far as the surface brightness limit, and also covers a much larger sample. So what Sophie has done is she's improved also her technique for measuring the size of the O3 features, and with a much bigger sample of now 200 galaxies at cosmic noon, was able to separate into a control sample that we don't believe have an AGN. It's not necessarily perfect, but then we have a pretty confident AGN sample. And these two montages are just a subset, but you can see now with JWST, we can basically isolate and see the ionized gas. So this is in green, which is dominated by O3. So there's a lot of variation in morphology, a lot of extended ionized gas, And then in the case of the AGN, we do again find some cases that are more like cones, like what we would expect. But with this new work, and this is now, by the way, this paper is on the archive, we were able to, and Sophie revisited the size of the ionized gas with the luminosity of the AGN relation. And then in this time, we actually matched almost perfectly the low redshift trend. So this means that already at cosmic noon, AGN can have a very far-ranging ionization range, and then it seems to be more important for more luminous AGN also already at cosmic noon. But however, not shown on this slide, but Sophie has also studied the relationship of these ionized regions with the galaxy luminosity and the star formation rate, and whether they might be starbursting, like if they have Paschen beta detection, for example. And there's still a lot of also ionized gas, as one might expect from the star formation. So still more work would need to be done to fully disentangle between these various sources. But it's still pretty exciting because we're pushing what we could do before with JWST. So with the DESI early data, we've already been getting insight several aspects of AGN black hole host galaxies. And then for AGN feedback, I think we still can and should continue to do case studies and statistical population studies. And I didn't get to talk a lot about machine learning, but I have backup slides if you want to ask me some questions about this. But what I really want to close with, because this is where I'm hoping we discuss, is revisiting the first questions kind of before and after this talk. So how did supermassive black holes form, black hole seeds? I think there's more and more interesting evidence from various studies now that maybe there are both light and heavy seeds that actually end up producing the population that we see today. Do we need to refine a bit more this question? Like, do we want to look at the proportion of the two different kinds of seeds? So I think I'd like to see if people want to discuss this. Okay, so next, when and how do black holes grow as far as triggering and duty cycle? We have seen a lot of progress as far as AGN identification. I didn't even touch this, but they are I think I have over 100 papers now that I've saved in the AGN identification library. So this is very popular because we need to find them to study them. And then making distribution functions, so lots of luminosity functions and scaling relations. So this work is normally held back by the limitations in survey depth versus also the survey breadth. Are we complete? Can we get rare objects? This, I think I would say, has been progressing along. Coming online soon, the LSST will definitely help as far as on the optical side anyway. And then with Rosita, we have very deep, very wide X-ray, a bit softer X-ray, but still very nice. So what's still missing? So I think one reason why there's still a lot of work with AGN identification is we're now using identification to find these finer classes that have astrophysical meaning. So it's not just saying broad line, narrow line. It's what can we learn from that? And I think this is one area actually where machine learning techniques can help us. But what's still missing, I think still the most obscured phases, and especially at high redshift. So there are still things that even JWST cannot do. So I don't know, is there a future mission that we can go still high redshift, but also obscured? That would be definitely something nice. And also, if anyone wants to discuss, also if you want to disagree, that's also fine with me. And then the last question I had at the beginning, how do they impact their host galaxies? So the question of AGN feedback. So by now, we find a lot of evidence of ionized gas. We also find a lot of evidence of multi-phase outflows. We find also evidence of very large scale impact, like these radio jets, like in galaxy clusters with cavities and so on. I think there are still some open questions about the energy coupling between the energy of the AGN and the actual impact on the ISM, so for the host galaxy star formation rates. So right now, I think we need to continue what we're doing as far as detailed mapping, but we need to do this at both low redshift, high redshift. So these IFU studies, for example, at high redshift are interesting. At low redshift is where we also can use time series and short time variability to help, because short time variability means a small spatial scale phenomenon, which means that we can basically observe phenomena that we cannot resolve like spatially with our observations. And I did not even touch this. And then, yeah, I think this is also an area where we probably need the close comparison with simulations to kind of close the loop of the feedback. And I'll stop here so we can have discussion time.
Thank you, Stephanie. This was fantastic set of big questions for us to consider and fantastic results you shared. So if folks have comments, questions, you can put something in the chat or go ahead and raise your hand. We can go ahead and unmute. Travis?
So yeah, Stephanie, thank you so much for a great talk. So right here, you say we need to check out the most obscured phases at higher redshift. Does that mean we would need a far IR observatory, or we need an X-ray observatory?
I mean, I think both can help. Like, for example, I think the Athena concept, which is European, has this is one of their cases, their science cases that they can do also because of, I guess the redshifting helps for X-rays and we get the harder X-ray. So even for obscured AGN, we can detect them still at higher redshift more easily than lower redshift. But as far as I mean, I guess my mind would go to kind of both ways, be like, okay, X-ray or the far infrared, like you're saying, because then we see the dust processing at least, because we cannot see a lot of the X-ray, and we probably cannot see any optical light. But that said, I think counterintuitively, but some of the optical light actually works well. Like the narrow line region can still work well, and even Compton thick AGN sometimes too, which is one part I think that's less intuitive. Like we lose the point source, so we lose the broad lines. But because of geometry effects, we might still be able to map ionized gas from narrow line region.
Well, but would you be able to do it at high redshift? We need heckin' high resolution then to be able to understand narrow line region geometries
I
then
think,
for like a typical Seaford type situation, right?
Yes,
So
because
yeah.
now with JWST, for example, this has been done. I think these are cases at redshift even 5 to 6 with a few, but it's like very, unique detailed case studies level.
Cool.
Yeah, so as far as getting a sample of those, I would say it's either a far IR mission or X-ray mission.
And then I had another question about so with all this work with DESI, and with Roman coming up, like, do you see any way to connect those two surveys together to maybe like is the GRISM spectroscopy with Roman going to be useful, or any other
Yeah.
applications?
So I haven't looked into detail of what the Gaussian spectroscopy case, but I do want to mention one thing that I have not mentioned is mostly for the question of AGN triggering. One way that we study this is we look at are the host galaxies like isolated galaxies? Are they merging? Do they have like tidal features? Do they have like a major merger versus even minor mergers? So having very detailed and deep imaging and morphologies and high resolution morphology is very important for this question. So for example, I think already with Euclid, like combining like spectroscopy from DESI with imaging from Euclid or imaging from Roman with all the overlap, I think can be used together to get like the morphology from the imaging and getting the redshift and also the source of ionization from the spectrum. And this is also one area where machine learning is now, I don't know if people have heard here the concept of foundation models. maybe I can use, I have one slide that like shows an example of that. I think that, oh, maybe I can leave this presenting mode. Yeah, okay. So foundation models are self-supervised, so so basically they learn the structure of the data just based on what's in the data themselves. And now for astronomy specifically, there's one that's called Polymetric AI released one that's called AON1, which is a very large foundation model that's putting a lot of data together. But for DESI with the legacy survey imaging right now, this model says, okay, this is an image and this is a spectrum of the same object. And then learn the representation of this and construct what is called an embedding or a latent space, which is the same thing that using basically transformer architecture. But in this case, with shared weights between the image and the spectrum. So Yufeng Luo, a graduate student at Wyoming, has built the first one combining for 2 million images and spectra pair for the training. And then the model learned on its own, like different properties. So for example, this figure shows, this is kind of a 2D projection. So this is similar to UMAP, but it's called PacMap. But it preserves the structure of the data, but the axes don't have like a physical meaning. But this foundation model called AVIS, both using the spectra and the images, now we look where they are. So first of all, it distinguishes between spectra and images at different parts of the space, even though they're like trained together. And then they're split between the spectral type from the pipeline, so galaxies in blue, and then quasars in orange and stars in green. So these are kind of naturally separated by the model. And then you might wonder, like, why are the galaxies in blue seem to form kind of cluster into 3 region rather than just a single one? And then the answer to that is it turns out that there are 3 kinds of galaxies targeted by DESI. There's the bright galaxies at low redshift, the luminous red galaxies, intermediate, and then the emission line galaxies. So this is all learned by the model. And then this model being a foundation model means we can then train a lot of machine learning tasks, like classification, outlier detection, finding redshifts, and then questions about, so what I'm interested in is like questions about AGN and their host galaxies. So it's a way that to include like all the data, including the imaging and the spectra. But we could even extend this. This could be adding X-ray information, radio information, etc. So when I mentioned earlier, I feel like with machine learning, we're not fully utilizing yet the potential is because we're just now being able to build these big models and capture all the data structure. And then I think this is kind of on us to say, okay, now how do we ask more questions and leverage kind of these new capabilities that we have? But this is kind of a separate angle compared to the question of what's the future mission that we need. But I think the dream is to basically use Roman data in here with the DESI spectra in here, and then adding also other wavelengths.
Thanks, Stephanie. Yeah, the potential there seems enormous. I'll also point out that Suarez included a link to the AI machine learning STIG talks and tutorials in the chat. So if anybody's interested in learning more about the potential there might be some good resources at that link. So Stephanie, we have 2 questions in the chat that I can read out. The first is from Arjun Suresh. It says, hi, Stephanie. Thank you for the talk. I was wondering if you know about any telltale observational signs of super Eddington accretion. Is super Eddington accretion a prerequisite for light supermassive black hole seeds to get as big as they do?
Yes, thanks for the question. So one category that I've heard as being maybe undergoing super Eddington accretion is narrow line Seyfert ones. So those as far as the observational signature, it seems that they have narrow lines and broad lines, but the broad lines are not quite as broad. And then this is normally attributed to having a lower mass black hole. So these actually tend to be below, like if we look at the black hole mass galaxy mass relation, they tend to be below with under massive black holes. So for that first part of the question, I would say kind of this is one example. And otherwise, yes, to measure the Dayton accretion, we have to make sure we measure properly the accretion rate and then the black hole mass, which is not always obvious. But so that's definitely one kind of observational category. And then as far as being a prerequisite for the light seeds, I think it's what makes the most sense because it's just they have so much, catching up to do. So if we start from these like small seeds, one of the ways that people put constraints on black hole seeds is also by looking for the highest redshift quasars and measuring their black hole mass, because at high redshift there's very little time since, after the Big Bang, we need to form a black hole and then grow it very fast. So that's also one approach to put limits on this. Okay, so should we go to the next question because I close it?
Yeah, so the next one is from Gianni Sims. So hello, thank you for the great talk. I was wondering if you will be going more in depth about studying different black hole growth models, for example, power law or AGN main sequence method, and if so, how will that be done?
Okay, so I'm not sure if the question is specifically for the DESI data. Right now, as far as black hole growth, there's a plan to make black hole mass functions as with the DESI data. And then let's see. So that's one plan that exists. And then aside from that, I think comparing AGN luminosities to star formation rates, as far as comparing like the relative growth of galaxy mass and black hole mass. And then if you want to elaborate a bit more or unmute, because I don't think I'm fully answering your question, but those are elements that come to mind.
Gianni, if you want to unmute, you're welcome to.
Sorry, can you hear me?
Yes.
Yes.
Sorry. I guess my when trying to elaborate if there's a way to or any plans to, I guess, test out different like black hole growth models with using DESI. I'm not sure if the question is clear.
Yeah, I guess we can. Yeah, I guess I'm not sure exactly what the predictions are from the models. Like one thing I was thinking is to test the Eddington ratio distribution, for example, using that as a test. And then this can be split. So with the statistical sample, we can split into different like galaxy morphologies or galaxy types even. And then maybe I'm still not quite fully answering, but if you want to also follow up offline after the talk, I'd love to make sure I can fully follow with you. But
yeah, I can I guess I can follow up outside of the talk since probably there's time constraint right now. So
great. I hope you guys can continue that conversation. We are past the hour, which is not a crisis, but if there are any last questions, be happy to entertain your question before we part. All right, well, a big thank you to you, Stephanie. This was a fantastic talk. You posed some great questions that I think we can continue to ponder, and hopefully we'll eventually get some solid answers to some of these questions. It does seem like we make great progress. That brings a lot of questions along with it, and we're not quite to answering these big questions yet, but we'll continue to make progress. I'll mention that please keep an eye out on an email. We'll announce our next Spotlight series talks, and then also any potential talk on the Astra focus. So if there's interest in the community to talk about mission concepts, so we would like to support that. So let us know if you have an interest. And our next AGN coffee for the early career folks will be on June 4th. And so I put the Discord invite in the chat box there. So again, big thank you, Stephanie.
Thank you
I hope
all. I
everybody
see the
has
nice comments on the chat. Thank you so much, everyone.
yes, it's wonderful. I hope everybody has a great rest of your day, and we'll see you next time.
Thanks. Erin, do you have a minute?
I do. Let me just stop the recording.